In this lecture, we're going to learn all about water demands. And water demands are basically the amount of water that a community is going to use. And we're going to be focusing on municipal water distribution systems. So your typical system that you would see in a city like we live in Newburgh. And so projects begin with an assessment of what those water demands are. And these municipal requirements are going to include, we talked about beneficial uses of water in a previous lecture, but things like domestic use, public use, which includes firefighting, commercial, which would include restaurants, hotels, potentially schools, etc. Light industrial, so light industrial means usually small square footage industry, possibly like a very small manufacturing facility or something that doesn't use a whole lot of water. We'll talk about this later, but major industrial use is usually separated out from municipal use, and losses. So if we look at this figure here below, you can see there's a house in the middle of it, and you've got a pipe running to the house with this flow coming toward the house. And in that pipe, you can see there are some leaks. So we need to supply enough water that we can still have enough left over after water leaks out of those pipes. Water distribution systems are under pressure, which means that when there are gaps or leaks in the system, the water is going to go from the pipe out into the surrounding soil or the groundwater, and not the other way around. You can also see that we've got consumptive uses accounted for. This would be things like irrigation of the landscape around the house, so garden watering, landscape watering, etc., not major agricultural irrigation uses. And then we've got the firefighting flows. And then, of course, we have the non-consumptive use that's going to happen in the house as well. And that non-consumptive use is going to include things like hygiene, laundry, cooking, etc. Most of that water goes back down the drain. And so we're not going to talk too much in this lecture about it, but on the right-hand side of this, you can see the wastewater that's leaving the home is going to be made up of that non-consumptive use that goes down the drain, plus we have this inflow and infiltration terms. We'll talk about these later in the semester, but this wastewater pipe is flowing under gravity. It's not under pressure. And so when you have leaks, you can actually have water that's, say, infiltrating down from rainfall or just groundwater that's infiltrating and inflowing into the pipe. Because the osmotic pressure in the soil is higher than the atmospheric pressure that's inside the pipe. So when we talk about wastewater demands later in the semester, we'll have to include infiltration and inflow as well. But today we're focused on the left-hand side, the water demands for the houses. So when we look at design flows for a distribution system, we are going to include plus, we're going to add consumptive uses, non-consumptive uses, leaks, and firefighting. And then later when we talk about sanitary sewers, we will include the distribution flow, system flow, distribution system flow, but then we'll subtract off consumptive uses, so the water that gets used in the garden, for example, is not going to go down the drain. We're going to subtract off leaks, because those leaks that leak out of a wastewater pipe, if that happens, they're not going to get to our wastewater treatment plant. We're going to subtract off the firefighting, because we're going to assume that the water used for firefighting does not go down the sanitary sewers. It'll probably wind up going down mostly the storm sewer drains or evaporating. And then we're going to add that infiltration and inflow from the surrounding soil. So not to worry about the stuff on the right hand side right now. Just note that when we're doing design flows for distribution systems, we're going to include all those things on the left hand side. Overall, though, when we start looking at water demands, typically the overall equation, I'm going to write it here in the lower right hand side. When we look at what is the overall demand, we're going to lump the consumptive and non-consumptive uses together, and so we wind up having the population, and we'll say the population at our design horizon. So explain that in a second, times the per capita use. So if we're designing a new water system and we design it for the population that our community currently has, next year it's going to be too small if our community is growing. And so we always want to say, well, how long do we want this project to last? If we want it to last 10 years or 20 years, we're going to try to estimate what will be the population in 10 years or 20 years and use that to scale up what the water use is going to be, and we'll design it for that. So estimating future populations depends on knowing what the population growth trajectory looks like. And you can see this figure on the bottom of the page here has a basic population growth model that has 3 different phases to this curve. In the lower part of the curve, you can see that we have geometric growth, also known as exponential growth. Okay, in that phase of the curve, the growth rate, or the derivative of this curve that we see here, the growth rate is proportional to the population. So the more population I have, the steeper that's going to grow, right? This is similar to if I say the population is growing at 5% per year. It's 5% of what is there, and thus the actual amount of people that we grow by each year is proportional to the amount of people that are there currently. We then enter this arithmetic growth phase here, where the population growth rate is constant. It's not changing with population. The derivative of that line is constant. And then finally you get to this declining rate of growth, where the population itself is still growing, but the rate at which it's growing is slowing down as you reach some saturation population. You can imagine maybe a place like Los Angeles, where the geography of that region constrains growth to some extent. Once the development kind of got out to the surrounding mountains, it became more difficult for LA to grow, and so the growth then happened with infill and increased population density and so forth. But eventually you can get to a point where the population growth rate is slowing down, or at least slowing down relative to what it had been previously. So mathematically, go to the next page, we have 3 different approaches to handling these 3 different phases of the curve. The first is the geometric growth rate piece. In differential terms, we can see that the rate of change in the population with time is equal to what we're going to call K sub P times P. In other words, how is the population changing with time? It's changing proportional to the population. The K sub P is a constant of proportionality. If I integrate this equation, I can integrate it and then rearrange. I'm not going to show the whole integration here, but we get natural log of P at some future time t is equal to the natural log at P sub 0, the current time, plus my constant of proportionality times t. Okay? So importantly, and we're going to get to this when we get to the example problem in a bit, this K sub P, we can think of this as the percent growth rate. So if I said, how many people, if I look over here at this left-hand side, what's the change in population with time? How many people will I have over this next year grow in my community? It's that percentage growth rate times the number of people that are there currently. Okay. The second part, the linear arithmetic, says d sub p dt, or dp dt equals, and here it's going to be k sub a. So k sub p stands for the constant of proportionality. K sub a is the arithmetic growth rate constant. Here, if I integrate this, I just get simple linear equation p sub t equals p0 plus k sub a t. And then if I'm in the declining growth rate phase, I get d sub p dt equals, and we have kd for declining, and then it's the psat, the saturation population, minus the current population. So the further I am away from the saturation population, the greater this second term is going to be, and thus the greater my growth rate is going to be. If I am really close to psat, this second term becomes close to 0, and my growth slows down to almost 0. If I integrate this, I get a little bit more complicated equation. P sub t equals psat minus, and then we have psat minus p0 e to the negative k dt. So as an engineer, I can use any of these depending on which phase I think that we're in. I can look at historical population records to try to determine which of those it is. But in reality, many cities and clients have planning documents that have proposed future zoning, parcels, etc. They have planning departments that do this kind of work. They're looking at how is our city going to grow, because that information, those projections, go into all sorts of things, from what should our tax rates be to what should our utility rates be. What about, not just water supply, but wastewater, transportation, firefighting, police. All of the functions of local government are dependent on how many people are in your city and will be there in the future. So often we can go to those kinds of planning documents to get a better sense. The United States Census also has lots of data from the past, but also projections for the future, so they have people doing this kind of work for you. So you're going to use whatever resources you have available to be able to project what the population is into the future. So that is all about that population side of the overall demand. Then we get to the per capita use side. And as we talked about in a previous lecture, in the United States, the total municipal use has fallen in the past 20 years. But also, the per capita municipal water use has fallen over the last 40 years. So even as population has continued to increase, total water demand has dropped, and therefore per capita demand has dropped. The current water demand is around 100 to 150 gallons per capita per day in the United States, but it varies from around 50, which is city of Portland, one of the lowest water use cities in the country, up to over 300 gallons per capita per day in areas like Utah and Nevada. But really, this is going to depend on things like climate and location. Things like metering. If you have water meters, people use less water. Believe it or not, not everywhere in the United States has water meters yet. Income levels. Tends to be that higher income levels use more water, mostly because of landscaping. Lot size. And conservation programs. All of these are going to affect the water use. So when you are doing this kind of work, you're going to look up the best data you have available for your area. Table 7.12 or 7.12 below provides additional detail. So just looking at this, we're looking at the left-hand side, the water usage, not the wastewater usage here. Couple things to point out. The individual residence and typical home, this guy right here, says that the range is 40 to 130 gallons per unit per day, and the typical is 95. We're going to use that in an example problem in a bit. But you can also see some commercial uses like office buildings per employee, restaurants per customer, schools per student, etc. So if you have nothing else, you can look at a table like this to get a better sense of the demands. All right, next page. Fire demands. So there's a lot of methods available for estimating fire demand, and every kind of local area might have their own. There are national fire codes and also state fire codes. So you're going to have to look at what you're supposed to use for the area you're specifically working in. But I've looked at about 5 or 6 of the different methods that are around, and most of them are very, very similar. That doesn't mean you can use any of them in any project, but if you learn how to use one of them, you'll be very familiar with the other methods. So I'm showing here the Sacramento County Fire Protection District fire flow requirements because that's what I was familiar with down where I was working in California, but most of the others are similar. Your book also has one in it that's also similar to this. It looks more complicated, but it's fairly similar. So what are the factors that you're going to look at when you're establishing fire flow requirements? You're going to look at the type of construction. You're going to look at the floor area. And sometimes, depending on the specific code you're looking at, the presence of sprinklers. If you have sprinklers, your fire flow requirements can actually be decreased. But the larger the floor area of the structure, the larger the fire flows are going to be. And then the types of construction, different types of construction have different kind of flammabilities. So if you look at this table, you can see, I'll try to show you how to read this. Let's start over here. If there's no requirements for fire resistance on the building, so standard building, nothing has been done specifically to make it fire resistant. These numbers refer to square footage, so from 0 to 11,300 square feet, the fire flow in gallons per minute is going to be 1,500 to 2,750, and the duration is 2 hours. Then 11,301 square feet to 20,600 square feet, the fire flow goes up to 3,000 to 3,750, and the fire flow duration is 3 hours. And then at 20,601 square feet and greater, the fire flow ranges from 4,000 to 8,000 gallons per minute for 4 hours. As I move to the left in the table, you can see the next one over has this little non-combustible and combustible structures in B. Combustible structures must have 4 hours fire-resistive exterior walls. So then the square footage requirements, they all go up, basically. So there's a greater chance you'll be in a lower category. And as I move to the left, all the way over to the left side of the table, non-combustible elements, structural elements, steel, iron, concrete, and masonry. Now I can go up to 70,900 square feet and be in the lowest fire flow requirement, the 1,500 to 2,750 2-hour category. Okay? So we'll do an example problem where we'll refer back to this table in just a minute. And then we've got industrial requirements. So I said it earlier on that light industry can get included into commercial or municipal requirements, whereas major industry, so say you have a huge employer in your town, big manufacturer of furniture or food supplier or something like that, those are going to be responsible for getting their own water supply usually. An example in Newburgh was the old paper mill. They had their own water intake and then their own discharge as well. As far as civil engineers and their kind of nexus with heavy industry these days, the most likely case, you might be working on a water supply project for them. You might also work on conservation, reuse, or recycling, or treatment projects. I have this example of the chicken processing plant that I'll show you in class next time we're together, that I worked on, where the work was associated with documenting the huge amount of water conservation that they had done in the chicken processing plant, to just document that they were doing their best to conserve water. They had gotten some bad press in an area that was very drought prone in California, and to comply with some emergency drought declarations that the governor had made, they needed to do this kind of work. So I'll show that to you next time. And then finally, irrigation demand. Mentioned that landscape irrigation around houses, that comes from the tap, and so it's going to be included in the water supply that the city has to provide. But irrigation demand, large scale for agriculture, we're going to be covering that in a different class. In engineering hydrology class, we talk about the methods for this, because it's fairly involved and quite complex. So your book covers some of that in chapter 1 and some of it in other chapters. But essentially it depends a lot on climate, on the type of crop you're going to grow, the specific kind of pattern of rainfall, evaporation, etc. There are very well documented methods for doing this, but they take several lectures to learn, and we're just going to handle it in a different class. All right, so let's do an example problem where we bring some of this stuff together. We've got a community, Newtown. It's located along a major interstate highway and only has 5,500 people, and it's expected to have a 2% growth rate for the next 20 years. It has a K through 12 school that has 800 students, as well as a large shopping center along the freeway that has restaurants that serve 2,000 customers per day and has 22 commercial restrooms besides. What's the current estimated water demand for this community? What is the estimated water demand 20 years from now? And what is the maximum fire demand? What volume of water would be required to fight that fire? Okay. So we're going to, as we do this problem, we're going to assume values from table 7.12 in the notes that we looked at earlier. We don't have any better data for this community, this made-up community, so we're just going to use that. So part A, current water use. We've got the 5,500 people that live in town. We've got the 800 students. We've got the 2,000 restaurant customers and the 22 commercial restrooms. So we're going to say we've got 5,500 residents, and we need to multiply that population by the per capita water use. And in that table 7.12, The typical value for that was 95 gallons per capita per day. We're going to add to that the 800 students, and the typical in that table was 25 gallons per capita per day. We're going to add to that 2,000 restaurant eaters, and the typical there was 9 gallons per capita per day. And we're going to add to that 22 commercial restrooms times 550 gallons per capita per day was what was in that table. So we do the math. First one, we get 522,500. Second one, we get 20,000. Third, we get 18,000. And fourth, we get 12,100. We add all those up, and we get 572,600 gallons per day. Okay, so that's part A. That's the current estimated water demand for this community, a little over 500,000 gallons per day. Part B, we're going to say, how about in 20 years? So here it gets a little tricky. We've got population growth of the people in town. We have to ask ourselves whether that's going to also increase the population in the school. And we're going to assume that it does. It kind of makes sense that if the town is growing, the school would grow as well. That the school's likely also serving surrounding areas in a situation like this, which might also be growing as well. But then we have to ask, will we have more customers per day and more bathrooms as well in the future? In this instance, I'm imagining that this shopping center is on the interstate, and while it's providing employment for lots of people in the town, no doubt, most of the customer base is from the people driving by on the interstate. You wouldn't serve 2,000 customers per day from a local population of 5,500 people. So while the town is growing, we might say, well, we're not going to assume that there's going to be more people driving down the freeway from, in 20 years. So we're going to keep those constant. Anyway, this is all just very speculative, but just showing you how you might do this. So we've got a 2% growth rate. And so that is going to clue us in that we're using a geometric growth rate model. And the K sub P is going to be 0.02. So we look at our equation. Natural log of P sub 20, population in 20 years, is going to equal natural log P sub 0, which is 5,500, plus my K sub P 0.02 times my time, 20 years. I do this math and I get 9.013. And so now to solve for P20, I just take E and raise it to 9.013, and I get that P sub 20 is 8205. We're going to assume student growth rate is same. So we've got natural log of the student population in 20 years is equal to the natural log of the current student population, which is 800, plus 0.02 times 20, and we get 7.08. Solve for S20, 1193. And like I said, we're going to assume that restaurants, restrooms due to interstate and R constant. So we've got our new population 8205 times our 95 gallons per capita per day, plus our new student population 1193 times 25 gallons per capita per day, plus the existing, so these two wind up being, the top one is 779,475, and the second one is 29,825, and then we still have the 18,000 and the 12,000, 12,100 from before. Add all that up and we get 839,400 gallons per capita per day. Not per capita, sorry. Gallons per day. So 839,400 compared to 572,600 today, that's a 47% increase in the water use. So like I said, if we had designed this system for current use, it would be too small very soon. All right, so the last part, what is the maximum fire demand and what volume of water would be required to fight this fire? I'm going to start a new page. Part C, max fire demand. We don't know the exact size of this structure or its construction details, but we're just going to assume it's a very large shopping center. We've got restaurants serving 2,000 customers per day, 22 bathrooms. That's pretty big. So, I think of like a typical large strip mall being something like 40,000 square feet. But we're just going to assume it's really large, no special fireproofing. And so we're going to put it in the largest fire flow demand category. The fire flow 4,000 to 8,000 GPM from our table for 4 hours. And then it says what's the volume of water that would be required. Well, if it was 4,000 GPM, gallons per minute, times 60 minutes per hour times 4 hours, we do that math and we get 960,000 gallons. Likewise, if it was 8,000, we get 1,920,000 gallons. So somewhere in that range, basically 1 to 2 million gallons is what's required to fight the fire. And again, we're just making assumptions. We don't have that much information. This kind of assumption making is common at preliminary stages of a design. As you get further into the design, you might refine those estimates as you get more data and more information, more detail. But that kind of covers the water demands for now. Hope that all makes sense. Next lecture, we'll talk about how do those demands look like over the course of a day and how do they change over the course of a year.